everyone. My name is Brianna Curl, and I will be your moderator for today's webinar on virtual prototyping using electromagnetic simulation for connected devices. Everyone's line is currently muted and will remain so for the duration of the webinar. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly during the webinar. With that being said, I want to talk a little bit about EMA Design Automation's partnership with Dassault Systemes. This partnership has the joint mission of connecting teams across a common data model for unified product development and collaboration. Together, we offer solutions to transform businesses by enabling the various departments within an organization, such as engineering, operations, manufacturing, and supply chain. Ability to easily collaborate and stay connected throughout the entire design process with access to the same data. This unified approach provides stakeholders with the ability to design, simulate, analyze, and verify true digital twin long before anything is produced, eliminating the need for multiple design iterations prior to production. Today, we will introduce some of the simulation and analysis capabilities Dassault brings to the electronic product development process. So thank you all for joining us for today's webinar. And before we get started, I'd like to introduce you to our presenters, Mathilde Himon, Derek Younes, and Mahesh Charaga. Mathilde brings a wealth of engineering and strategic product vision. She helps high-tech manufacturers accelerate development and increase device reliability by maximizing the use of virtual validation. She will be setting the stage for today's webinar by discussing the industry's history and its challenges. Derek is a trusted sales professional with extensive experience presenting, selling, implementing, and supporting engineering software solutions. He works strategically with channel partners to showcase simulation technologies within the Simulia product portfolio. He will be discussing the electromagnetic solutions. Mahesh uses his extensive experience to bring a consultative solution to help clients with digital transformation and product innovation. He brings simulation solutions to customers in a variety of industries such as aerospace and defense, automotive electric vehicles, and industrial equipment, to name a few. He will be wrapping up our presentation with device structural and thermal performance. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now over to you, Mathilde.
Thank you very much for the introduction, and welcome everyone to this webinar. I'm Mathilde Himon, Solution Manager from Dassault Systemes, and today my colleagues and I will introduce the highly virtual prototyping solution, the Dassault Systemes simulation solution for high-tech companies that can help your customer accelerate the development and the development of their product, and also increase the reliability of your product using simulation. So we'll start with a few words on the high-tech industry, its industry business drivers, but also the challenges in terms of simulation. So to start, I guess we're all pretty familiar with the high-tech industry because we all carry around many connected devices all the time. But it's not only about the connected objects and devices, but also about all the components and the electronics inside all products and all devices we have today. And what OEM have in common, so connected device OEMs and electronics OEMs have in common, is that they face a huge pressure to innovate because the high-tech market is a highly volatile market. The consumers' expectations are evolving very rapidly. They're always looking for new features and form factor. And poor product experience, or even worse, an early product failure can have catastrophic outcomes on the company's revenue and also reputation, because high-tech consumers can very easily turn to competition. Moreover, to answer to the market thirst for innovation, OEMs have to engineer more and more complex products with an ever-increasing components density and ever thinner and lighter design. The foldable phone you can see here in the screen is a good example. Imagine how complex it is to have all the high-power electronics going through the flexible parts, and also to have a phone robust enough to resist 100,000 volts. Finally, the high-tech industry is characterized by a short design cycle, to compare to aerospace and automotive industries, for instance. Companies introduce dozens of new products every year and one new version of each product. So they face a huge pressure to accelerate their product development and to be first on the market. So what can help those high-tech companies face those challenges? Well, simulation. Simulation is key to avoid time-consuming and costly prototypes and also to ensure product reliability and performance. But it also comes, validation and verification also comes with many challenges. Because as I just said, high-tech companies have many product lines, but also with many product variants, and in some cases engineer their own components. So they need to verify all those system and subsystem in all domains, so electromagnetic, thermal, and so on. So imagine the huge number of tests and simulation that needs to be performed. Products are also defined by an important number of customer and regulatory requirements, but some performance indicator can actually affect, and in some cases badly affect another one. For instance, we all want more connected devices with Bluetooth, Wi-Fi, 4G, and soon 5G, but we don't want interferences appearing, or for example, the radiation absorbed by the human body increasing. So how can we ensure the best trade-off, but at the same time that all requirements are verified? Finally, discipline experts often work in a disconnected manner with an heterogeneous landscape of tools, methodologies, data formats. So this could result in the loss of data, but most of all in the loss of time. So how can we ensure continuous and rapid validation? Well, the answer is the Simulia simulation portfolio that integrates Multiscale's Multiphysics tools that are either integrated in the 3D Experience platform or on all the other standalone tools. This hugely improves the overall productivity because you can connect all discipline experts and all designers in one and unique environment, and also manage all your simulation data at that same place. So you eliminate rework and really accelerate your product development. And based on this portfolio, we have defined the highly virtual prototyping solution. So you can see an overview here that goes all the way from planning the validation and verification strategy, all the way through executing the different simulations, so electromagnetic, thermal, structural, all the way through building some multidisciplinary processes to find the best trade-off. So you can explore the design space and automate your simulation work. So I'll now let my colleague continue with a deep dive on the electromagnetic part of the simulation. So please, Derek.
Thank you very much, Mathilde. Welcome, everyone. Brianna mentioned it briefly, but my name is Derek Nunes, and I work at Dassault Systemes. And what I'm here to talk about is a little bit of a deeper dive into Dassault Systemes 3D electromagnetic simulation technology to give some examples, some details, and kind of give you guys a peek under the hood. So in light of that, let's get started. Why are we here? Why simulation? Why is this important? We can talk about it at a high level, but I really want to break it down into 4 key ones as I see it for EM or EMAG. And the first one is late stage failure. Now, we've all seen examples in the news where electronics can possibly start smoking or even spark, catch on fire due to thermal problems. Now, that is something that can easily be avoided if you are understanding what's going to happen earlier on. You're sending too much energy somewhere and it can't handle it, it's going to cause a fire. It's what energy does. So it's something that if you have even somewhat of a simple workflow, it's easy to avoid. and it all has to do with understanding things virtually before you actually build them. Not all publicity is good publicity, so we can put it that way. The next one is smart testing. Now, this is all about reducing the number of iterations and the amount of physical tests you need to do. Physical tests are time-consuming, they are costly. It's something that every company that is building a product wants to limit. It's going to up the speed of your go-to-market, the quality of your products, and maybe most importantly, it's going to lower your costs. Now, there's going to be a central theme here, and that's because you understand things so early on. You're not having to do something that I'm going to talk about in this next one when you improve the product quality. Now, this is for rapid testing. This virtual exploration and innovation allowed you to avoid what I like to call the build, test, tweak workflow, where historically engineers, because they didn't have a choice, had to build something, take it in the lab, it's not working. Okay, so why isn't it working? Now we got to figure that out. Sometimes you need a physical test to figure out why it's not working in the first one. If you have this visualization and understanding so early on, your concept design prototype kind of wheel you see there is much more fluid, it's faster, and maybe most importantly for me, because this is really all about high tech, you have time to get more creative. I mean, the thing about high tech is you want to be cutting edge. You want to have something better that's things that people haven't thought of in the industry. So it's really quite critical. And the fourth one is pretty straightforward, quite honestly. It's regulatory compliance. Now, in the electromagnetic world, what we're talking about there is we're looking for something called EMI. That's electromagnetic interference. Now, that's talking about unwanted signals. That's really all it means. If there's EMI, it's bad. That interference can, they're not going to let a phone go to market. That makes it so your phone doesn't work. There are strict FCC standards there that need to be passed. So in this slide, I wanted to put in just because that highly virtual prototyping workflow is fantastic, but I don't want to limit the scope too much because Dassault Systemes 3D EM simulation technology is so extensive that I want to hit on a few more things here. So we're going to talk about antennas, we're going to talk about sensors, but we can do a lot more than that. We're talking full level circuit board, cables, GPS, RF connectors, radar and radar cross sections, circuits, and this list could have been so long it wouldn't have fit on the slide. And a good example I want to use going back to the simulation aspect for physical testing is that image on the bottom center. That's a CST Dassault Systemes human biomodel. That's something you can't physically test when it comes to SAR, specific absorption rate. That's the EM effects on the human body. Now, we don't want to find out, oops, it was turned up a little too high and we fried that person's brain. We don't want to hurt anybody. So having the ability to test that early on is just such a great example of why simulation is so important early on in the design stage. But the overall message is that we can do anything electrical that you can think of. That's the reality. So. And I want to bring the audience today in on the ground floor with us to really give you a peek under the hood of what I'm talking about here when I say Dassault Systemes 3D EM simulation technology. Now, for 4 years, and I guess technically I still do because we became Dassault Systemes, I worked for a company called CST, Computer Simulation Technology. That made some of the most powerful 3D EM simulation technology on the planet. For multiphysics, really anything you can imagine. That is the Rolls-Royce engine of this entire workflow. That's what's driving it, and it really is as good as it gets. It's fantastic technology. I feel lucky to have been able to sell it. The reason it's so good, in 2 words, if you take anything from my portion, please take this. It's that it has complete technology. It has every tool in the toolbox. If you're building a highly resonant or narrowband antenna, let's say, you're going to want to use our frequency domain solver, for instance. Now, if you're doing something broadband, or electrically large, you'd want to use our time domain. Each of these numerical methods has a different use. They can be a yin and yang of each other. Usually what one is good at, the other is not quite as good at. It's just kind of how the world works. So having 17 provided by default in our base package is really quite incredible. And on top of that, it can handle everything from statics, 1 hertz, up into the optical spectrum. You're always going to have the right tool for the job. You know, we have optimization, you can import whatever CAD, all the normal things. The meshing's fantastic. I don't want to go too deep into that, but the example I like to use is this is about avoiding, for engineers, the brute force approach, the brute force method, which is having the wrong tool for the job. So the example I like to give is you could pound in a nail with the butt end of a screwdriver into a piece of wood, but you'd really rather use a hammer. If you have every tool at your disposal and you know when to use them, then you can do the best possible job, use the least amount of hardware, be the most efficient, effective, and fast. To set the stage just a little bit further about the world we live in, a lot of this stuff we all know, but I still want to address it, is 3 things about the electrification of our world, because it is happening. No one can stop it. It's here. It's been here for a while. And the first one is variability in product complexity. So if you think about how phones used to look when there were giant bricks and you had to pull the antenna out like 2 feet, now we have mini supercomputers that we can fit in our pockets. That means that there's a ton of electronics density, which has its own unique challenges and problems. Now, especially in the high-tech industry, that is not going to change. That's going to increase. So simulation's only going to become more important as far as that's concerned. Now, the second thing is the Internet of Things, IoT. This is things that we've terms that many of us have heard, but every time I hear this term, really what I think is antennas on things. That's all it means. The Internet of Things means connectivity, and if you think connectivity, that means antennas, just flat out. That's all it means. And without that, I wouldn't be able to do this, speak on this webinar right now. That's how it's working. That's how critical it is. So, and that's only increasing as well. And now it's on watches. Our fridges. It's getting kind of crazy actually. So, it's even more important. And the third is autonomous and smart devices. Now, a practical example I want to use here is, let's say, a self-driving vehicle, for instance. Now that could be using a GPS antenna, let's say, to navigate the roads to get to the destination. But what happens if a car pulls out in front of it? That antenna is not going to be able to read that. That's where you would need a sensor. The sensors are let's say, the eyes and touch of electronics. It turns into electrical signals, whether it's distance or weight, whatever it may be, to measure some sort of physical stimulus, whereas antennas, as I mentioned before, that's more the mouthpiece and the ears, how things communicate. So all of these things need to work in conjunction and are critical to coexist. So building off of sensors a little bit here, I just mentioned that it's measuring a physical stimulus, right? So I'm going to use phones as an example kind of over and over here. It's high tech, but this is showing a touch screen on a phone. Now this is something we do every day. I'm swiping up and down to read emails. I'm clicking that like on social media, whatever it may be. That is all made through capacitance with a sensor on your phone. This is something that we may not even realize so widely used, but they're everywhere. They're in your pocket. So this is a good example of how sensors are so important to us, maybe on a daily basis, some for fun, some to make sure that your business stays up and running when you might not even know, because you need people to have a working phone. And antennas do need to function well in a vacuum, let's say in an anechoic chamber, where you need to measure the gain, the impedance, look at the near fields and the far fields, the directivity, the lobes. You want to visualize it. That's all great. But what happens if you see that, the 2 red radiating antennas up at the top? What happens if you need to move that down an inch because corporate wants to make some mechanical change to the phone, so you have to? How do you know that all that testing you did isn't completely out the window? Are you able to place it where they want you to? And how is that going to affect the installed performance of it? And not only that, when it comes to co-site interference, how, I was talking EMI before, unwanted signals. You don't want things to radiate or turn into antennas accidentally or interfere with each other. This is all critical and really, really, really important when it comes to rapid design cycles, getting creative, and being flexible. And to touch on EMC a little bit more, because it's very critical, I love this slide because it gets right to the point. Around 50% of electronic products do fail to meet the requirements the first time they're tested. And the real challenge here is, except for the optical spectrum, which is ironically the only way anyone sees anything, is electromagnetism is invisible. Now, EMI is all about radiated susceptibility or radiated emissions. Are you the villain who's radiating too much? Are you the victim who's too susceptible? Now, if you're putting them in these test environments, it's easy to test, yes, we did not pass, but do you know why? Where is it leaking in, or where is it leaking out? When you can have a tool to quickly visualize where this is happening, this could be a day's work, maybe instead of a month's. I mean, it's really, really important. And you're not going to go to market if you're not passing these requirements. You're just not. Sometimes it's not just a slow go to market. It always is if you're failing this over and over. But if you can't figure out the problem, you're not going to go at all. And that could be real panic mode for some companies. You never want to be in that position. So a nice example of this, again, I said I was going to use phones a lot, is you can look it up if you, use the sensors to swipe through your phone to look at the FCC requirements there, or you can kind of go to take out the battery on the back and see it there as well. This is every single phone that we have has passed these, and that's why we can all walk down the street and make calls with little to no problems. And just to wrap up my portion here, this is just a nice example using Dassault Systemes, prize CAD package SolidWorks, just to show a quick example of how we play well together with CAD. Now, this is an important one because our R&Ds are the same. So SolidWorks actually has a bidirectional parametric import with CST, where if you're making changes to the CAD in either or, it's going to make changes vice versa. So you have a person who's really good with SolidWorks, and you want them building your models in an efficient way. They're just great at what they do. But as the EE, or the electrical engineer, you need to run the analysis. It's not so iterative where you're just having to pass back and forth and really make it more painful than it has to be. It's all about fluidity and a good flow and everything playing well together, which is something CST is actually known for. So I wanted to point this out just as a quick example. And in light of that, I will pass it back to Brianna and Mahesh, and thank you so much.
Thank you, Derek. And with that being said, over to you, Mahesh.
Thank you, Brianna. Building off of what Derek talked about the bidirectional parametric import between SolidWorks and CST, I would like to add that our solution has a strong interoperability with multiple CAD solutions, not just SolidWorks, including CATIA V5, NX, etc. So the slide you see here, it basically represents, I apologize, it's a little bit busy, but it basically represents the openness of the 3D Experience solution that Method was talking about. This is based upon a single data model, providing a very strong CAD and CAE interoperability. What that means is, by leveraging a single CAD representation, you can seamlessly switch between analysis and design as you do multiple design iterations leveraging multiple physics. Our Powered by solution also brings the capabilities of the platform, the data management, the process execution, and collaboration, all those to the traditional users of the tools like CST and multi-body simulation and many other third-party tools. So we also have what we call process adapters or model connectors, which enable you to connect various third-party tools across MCAD, ECAD, CAE, and build workflows that involve these multiple different tools, and then do automatic execution using our process capabilities. So with that introduction, I'd like to talk a little bit more about the device structural and thermal performance. So the device structural performance solution is powered by Simulia Abacus technology, which can accurately predict the behavior of complex consumer electronic devices, leading to product designs which are robust and when subject to accidental misuse, as you see in the video here. In addition to predicting in-use behavior, the device structural performance can also be used to optimize component manufacturing and product assembly. So going through some of the workflows that this solution enables here, by doing component manufacturability, for example, you can reduce your manufacturing costs by 20% or more. By leveraging the device strength and stiffness, water immersion, drop test, fatigue and durability, we can reduce physical testing and reduce the field failure rates associated warranty costs as well by 50% or more. And the result is that you can accelerate your time to market from years to months. Going a little bit deeper into the solution, as all of you know, high-tech devices have a wide variety of materials in a very small enclosed space. Our comprehensive technology enables accurate modeling of these materials from metals to plastics, elastomers to adhesives and glass, to name a few. The animation you see in the middle of the screen shows the ball drop on an LCD screen, where the simulation is basically predicting the crack initiation and propagation of the screen very well. In addition, we have a new application called material calibration application that enables you to take your material test data and convert that into simulation material properties to plug right into the simulation to simulate some of the workflows that we talked about on the previous slide. And no design of high-tech device is complete without taking into account its thermal performance. So it's really critical to have optimal thermal response for these high-tech devices. So using our device thermal performance solution, you can design thermally efficient devices and subsystems for a full range of operating conditions by exploring optimal cooling strategies, leveraging CAD embedded CFD. So going through the different workflows here, you can quickly improve the thermal performance of individual components using during the conceptual design phase. And then you can accurately predict the thermal response of complex PCB layouts, leveraging the full translation of ECAD data to MCAD. And then you can improve the device structural performance under thermal loading by easily applying those CFD loads onto your FEA models. And finally, you can improve the device reliability with better thermal design by predicting, for example, fatigue life under thermomechanical cycles. So in essence, with this solution, you can significantly improve the overall customer experience, meet the regulations around thermal and EMAG, and then avoid lawsuits associated with safety standards. To put it all together, imagine having a single CAD representation of the design available to multiple teams for rapid trade-off studies over multiple design concepts and different physics disciplines. Method was talking about earlier in the multiphysics, multiscale slide, where you can seamlessly go between different scales as well as different physics from EMAG to structural to thermal. So in this example, we basically have a phone in a CAD like SolidWorks, your favorite software. And then you can basically, the EMAG engineer can take that CAD representation and quickly build an EMAG model and look at the antenna performance. With the default model, the performance was not acceptable, so the aluminum frame was changed to a plastic frame, which improved the antenna performance. Then the structural engineer takes that same model and then quickly does the structural analysis where they find that there is loss of stiffness. So you can easily modify the design by increasing the thickness. And then the thermal engineer can take the same model and then make sure that the thermal requirements are met as well. So this whole process using our 3D Experience platform enables a rapid interdisciplinary evaluation of design options, whether you're running hundreds or thousands of designs, and reduces the time from months to days. So I'd like to summarize what we discussed so far. Early on with the CST Studio Suite, Derek talked about how we have a one-stop comprehensive technology that can address all your electromagnetic needs and how it helps to avoid late-stage design failures and reduces risk, and more importantly, achieve the regulatory compliance that you need to put these high-tech devices on the market. And then we learned how the device structural and thermal performance solutions help you to make early and collaborative design decisions with fast and accurate solvers powered by Abacus and our CFD solvers. We also discussed the advanced material models that are available for these complex high-tech devices, and then how you can enable rapid interdisciplinary design of various options and then reduce the time taken from months to days. And finally, we touched upon this a little bit, where we have full interoperability between CAE and CAD, where you can actually leverage a single CAD representation across design and simulation and collaborate across teams that are dispersed geographically. And Derek also talked about the strong bidirectional parametric interface between CST and SolidWorks, and also other CAD packages like CATIA V5 and NX. And finally, we didn't touch upon this a whole lot, but as you saw in the earlier video that I played, we have this completely integrated simulation process and data management solution that basically can help you manage the entire workflows and the processes as you go through these design iterations and as you optimize your products for robust performance. So that's pretty much what I have. Thank you for your time, and if there's more interest to go deep dive on any of these topics, we'll be glad to do a follow-up. Thank you, and over to you, Brianna.
Thank you, Mahesh. At this time, I'd like to open the floor up for the Q&A. So please enter any questions you have into the chat now. If we're unable to address your questions immediately, we will be in contact with you. So our first question is, can CST handle optical applications?
I can take that one. This is Derek. Yes, definitely. Our time domain solver actually is really, really good for high frequencies. So that wouldn't be an issue at all. No, we can do it.
Thank you. So our next question is the CST a simulator for EM emissions and immunity?
Yes, absolutely. So if you're, it depends on how you want to set it up. Whether you're saying like the victim or the villain, you can do for radiated emissions or susceptibility easily. Very, very effectively.
Great, thank you. What else we have? Does CST have technology for electronics cooling?
Once again, yes, we have a thermal solver in the tool. There's a specific one called our conjugate heat transfer solver that's specifically made for electronics cooling. So that's a very powerful one, so we can do that as well.
Oh, thank you. Another question we have here is, let's see. Can CST simulate batteries' response to time?
It would depend on the complexity of what exactly they're looking for, but I'd be happy to follow up on that too. But I'm 99% sure yes, but would like to double check.
Great, thank you. Another question we have here is, can it do solenoid design, electromagnetic force?
Absolutely. So we have some specific technology for low frequency applications. It can do the magnetic force. That is on the lower end of the frequency scale, but we have not only our own proprietary technology, we actually acquired another company called Opera to enhance that. So very, very powerful stuff there, even more so the last year than the year before where it was already good. So
let's see what other questions we have. Can the CST solver assist with determining shielding effectiveness from a SolidWorks model?
Yes. Yeah. I mean, as long as you have the material properties, I absolutely.
Let's see what else we have. A few questions coming in.
These are great questions.
Yeah. How long do simulations take in the EMI radiation and conduction areas?
That's a really good question. I'm going to be kind of a politician on this one. It depends on the frequency. So the higher the frequency and the larger the structure, the longer it's going to take. What I do know is that we actually have some really specific technology for EMI within our time domain solver. It's called TLM, which has an octree mesh that can reduce mesh sizes by up to 90 to 95%. So it would be, let's put it this way, it would be quicker than the competition.
Great, thank you. Our next question is, can it show wireless charging and possible sources of interference?
Absolutely. Absolutely. Wireless charging, another usually typically low frequency application. Very, very interesting, very new, something we use, or people use CST for often. And we actually have some probably good materials and examples of that as well, if they were interested. Some nice graphics and stuff, if they wanted to follow up.
Great, thank you. We could probably follow up with them as well. Let's see what else we have.
I can definitely follow up on the question I was unsure of too. Oh, sorry, continue.
Yeah. Can it simulate lightning strikes?
Absolutely. That, when I'm trying to explain, like if I'm actually in a sales process and they're asking how powerful it is, our TLM solver is probably the best method on the planet for lightning strike. It might be one of the reasons why at a lot of defense contractors we are so prevalent, because lightning strike is kind of inherently transient. A lot of different frequencies. We can do it so well. That's the real answer. We can really do lightning strike. And we have a plethora of materials to follow up on that. Even some videos showing us doing the active simulation of lightning strike. A really incredible technology for that. It's one of our staples, actually. That's why I mentioned trying to sell this stuff. It kind of drives home the nail of how powerful the tool is.
Thank you for that answer. Let's see if we have any other questions. How about transformer low frequency design?
Absolutely. That's going to kind of go to those same solvers using on like the solenoids, like the magnetic lifts are static and our low frequency bundle mixed with Opera. 100%. Motors, yes. I know this sounds really repetitive, but it's true. And again, we have a lot of cool stuff to send about that because it's such an emerging market for motors. When I was talking about how we can handle everything from 1 hertz up to the up to terahertz, petahertz, that's a really big emerging market, and we have some great technology there.
Great, thank you. We have an attendee wondering if there's any sort of trainings available to learn more about these products and capabilities.
Definitely. There's definitely trainings that you can go to, scheduled ones, but just due to the nature of the world today, we definitely still have some ones online. I would encourage them to reach out, even if it's just general interest and they're just like, I'm just curious to see if it can do this. We're always looking to show the tool off. So if they had any, we could do a scoping call and then kind of figure out what they're most interested in and kind of do like a 45-minute to 1 hour demo showing even where you click the mouse. It's a really intuitive interface, so we like to put it in front of people. So both options are available. Sometimes training may cost money, and I guess I'm giving you a little cheat here. If you just have general interest, I'd say start with a demo, and if you're really trying to learn this tool practically, then get a training.
You mentioned charger particles and vacuums. How is that simulated?
Ooh, you're asking me about particle simulation. We have a particle and cell solver, our Wakefield solver. We have a lot of specific technology there for particle simulation. Now, answering that question and how is it simulated on this call might be a little lengthy, and it's a little much for me to bite off, so
Okay.
bear with me, I apologize.
We still have a few more questions coming in, but at this time we are going to wrap up, and if we did not get to your question, we will be responding and following up with you guys individually. And I'd like to thank you all for joining us today, and I hope you enjoyed it. And thank you to our presenters.
Happy to.
All right, I hope everyone has a good night or morning or wherever you are in the world.